So we want to go even further inside the wall. Watch with me. Inside the walls. Here we are. I wanted to know, so I went up to Wikipedia and I said, hey Wikipedia, how does power distribution work in your opinion? And they gave me this picture and it's pretty, right? There's a generation station, there's a step-up transformer, and this is the weird thing. We want to understand why there's a step-up transformer because these are expensive. You want to build a big box and paint it gray? That's going to cost some money, right? So they're getting up to extremely high voltages. These voltages could kill a man. I tell you what, you walk within a half meter of those and you'll be killed. Wow, assuming you're in contact with the ground. Also, if you flew up on top of one and landed like a bird, you'd probably be okay because it's all about voltage difference. Anyway, then you gotta have, oh man, if you're gonna go to high voltage and you don't want little babies to stick their fingers in and die, thanks, appreciate that. Then you gotta have a step-down transformer as well. Step up, step down, and then you've got customers over here, and the customer always knows about these gray boxes that are floating up in the sky. I call them the gray trash can floating in the sky, and I've got one near my house. And that brings us down from a certain voltage to here. So I'm just going to, I kind of translated this into my own. Thanks, Wikipedia. Let's get realistic, though. It actually looks like this. There's a loop inside of a magnet, and that's what the power station is doing. I don't care how you're spinning it. What are you, burning coal and having the steam expand and spin this sucker around in some kind of a turbine fashion? You got yourself a wind turbine? Did you hire bums on the street and say, hey, crank this pedal, tough guy? Well, that's not cost effective, but it's a nice humanitarian effort. Then you got this step-up transformer. I don't know what the voltage is right here, but I don't care. They're getting to a voltage that let's just go crazy. They're gonna say this voltage right here, where I'm taking the voltage between one wire and the other wire, they're calling this voltage, let's go crazy, let's call it 765,000 volts. This would be the largest cross-country transmission line voltage. And then we get to a substation. So it's finally gotten to my town, and at that substation there's some chain link fence, and inside of it there's another transformer, and that's taken us from a high voltage back down to a lower voltage. And let's say that this lower voltage right here, we're gonna go to right there, and we're gonna say that that lower voltage, what did Wikipedia say? It was something cool. Wikipedia said something like, oh man, I totally forgot what they were gonna say. Hey Wikipedia, sorry I offended you. Let's call it 4,000. Let's say that this voltage here is 4,000 volts. And I know that I'm getting two different wires and they're 240 volts apart from each other, but I'm only gonna plug into one of the wires into the ground, so I know I'm fudging this a little bit, but I'm gonna say right at this gray trash can in the sky, after the substation has gone right outside my house, and seriously, these trash cans are serving, 1 to 5 houses, depending on how your neighborhood sets it up. That voltage there, and I continue using purple, I guess, because that's what I'm doing. That voltage between here and here is now going to be 120 volts. And it's AC and it's doing all kinds of things. Yeah, I got it. I'm totally simplifying unfairly. At this point though, I want to pretend like there is only a hot plate on the entire circuit and this electrical distribution structure exists for me to cook ramen noodles, because that's what I'm eating. Here's what we get if we assume that this hot plate is the only thing in the line. I'm saying that there's a current right here, and that current is probably going back and forth, and that current is equal to, what did we have, 8.40 amps. And I noticed that the voltage right here, this voltage, only 113 volts. Now, I know that power lost in a circuit is I squared times R. And so I'm losing some power right here. Do you want to figure out the power of that hot plate? Let's go ahead and do it. If I'm trying to find this power lost for hours, it's going to be the current, which is 8.4 amps, and I'm going to be, let's see, 8.4 amps, and I square that sucker, and then I multiply it by the resistance. We had calculated just previously that the resistance of the hot plate was 13.5 ohms. Cool, so I find a power of 953 watts. Watt is the unit of power? What are you talking about? Yeah, you heard me, fine. Okay, so that's my power right here. And folks will be asking me questions like, yeah, but isn't there some power lost in distribution? And that actually is the reason that we use a high voltage right here. Let's assume, for the sake of argument, that this wire is very, very long. It's a big distance between the step-up transformer and the step-down transformer. So as a consequence, although the wires are beefy thick, they are also very, very long, and long wires tend to have more resistance. So let's give ourselves a resistance measurement. What do you want to say here? That this resistance is something like 10 ohms. Ew, gosh. I hope it's not that much, but it might be. And let's say that this resistance right here, and by that I mean the resistance between here and here is 10 ohms. Let's say that this resistance between here and here is 2 ohms. And I want to find the power loss here and the power loss here. But we're going to have to be much more careful than we've been in the past, because something made this go from 120 volts to 113 volts. I guess that means that this section of wire right here has some resistance. Remember, we called the resistance of the wire, we ended up calling that 0.83 ohms in this section that was within the school or within our home. That's that resistance right there. So some power is being lost in that line. And what really troubles people, when I get questions about this, people are asking me often about this equation. They say power is power loss. Sure, you can give me the I squared R trick, but it's all trickery because I know that power is V squared over R. And they say, yeah, but isn't the power loss in this high voltage transmission line, that's 75,000 volts. Dang, that's a really big voltage. Won't that be an enormous power loss? And doesn't that widely disagree with the power loss that you're saying? Because I usually argue like this. I say power, the power delivered to the substation, for instance, is the current times the voltage. And so my argument goes like this. The reason we have a high voltage line is because if I need to deliver power to a hot plate over here, I need to deliver power to that hot plate, and I need that power to be delivered, period. The customer is going to get 953 joules every second. That power is going to be delivered, so I've got two options. Broadly speaking, I've got an option where I have a very high current and a very low voltage. That sounds safe, but high current means high power loss. Or I could do a very, very high voltage and a very pathetically small current. That might be nice because according to this law, the Joule heating equation, we're going to get a very small power loss in the distribution line. And we need to get prepared to answer the concerns of the people who say, yeah, but power is V squared over R. Let me just really quick summarize my argument against using this equation. It's valid, but you better know what you're talking about. Remember here, we had a voltage drop of 120 at the transformer and only 113 when we get to the hot plate. You need to pay attention to the voltage drop in the line, not the voltage drop across the load. So up here we could say the voltage drop across the load is 765,000 volts. You better not plug that in right there. You better plug in the voltage drop of the line. So let's find the voltage drop in this line right here. We're going to assume, first of all, that the hot plate is the only thing connected in my entire city. This would be a good day, right? Everybody's coming over to get ramen at my house. Okay, how are we gonna get this voltage drop across this line? We're going to have to find the current that's going through this line. First, we say the power going through this line must be the same as the power going through this line, because I'm talking about energy now. There's a hobo spinning this sucker. They're generating some power. It's going through these lines, going through here, and the power is going to here, except for the amount that's lost. But the power that needs to be sent through this line is that right there. And if I do a little bit of calculation, I'm gonna find power, ew, gosh, I hate that. Power is current times voltage. So I'm gonna try to find the current through this wire right here. That current is going to be the power, which is 953 watts, forgiving for a moment any losses in this section right here or that section right there. Those will be small. The power is, the current is that power divided by the voltage of the line, and that's 765 953.000 volts. Here we go. And I'm supposed to take that 953. I'm going to be finding the current. Oh my gosh, that's not a lot of current. 953 watts divided by 765,000. Enter. I have got 1 milliamp going through this high voltage distribution line. That current is 0.0012 amps. Okay, it's a very small current going through here, but remember we have a resistance of 10 ohms because it's a really, really long line. That's what I proposed. So I'm going to try to find the voltage drop right here. Voltage drop on 765 kilovolt line equals current, this guy right here, through the 765 kilovolt line, times the resistance of the line. Be very careful to use the resistance of the line, which is this number right here, not something like the resistance of this line or the resistance of the load or the resistance of this line over right here. It's only that matters. I'm taking the current and I'm going to multiply it by the resistance of the line, which is 10 ohms. Oh my goodness. The voltage drop on here is, wait for it, that voltage drop is 0.0125 volts. What that means is if I take a voltmeter right over here on the opposite side of the line, once the drop has occurred, that voltage is going to read 764,999.9. Oh my goodness. And then I get finally, an 8 and an 8, 988 volts. Yeah, so that's the voltage, that 1/100th of a volt, that's the voltage that you need to use if you're going to use this equation. That power loss in that line is that very extremely small voltage square. Let's take that and square it. I'm taking that very small voltage drop, that was that voltage drop right there, which is 1/100th of a volt, and I'm going to, let's do square it, and divide it by the resistance of the line, which is 10 ohms, and the power lost in my line, thank goodness it's really small, 1.55 times 10 to the negative 5th watts. This is very good news. Shall we run a corollary calculation? No, I want to just find the power loss by this calculation right here. Instead, I'm going to take that current. Remember we had the current going through there, and that was 0.0012. I'm going to take that current and I'm going to square it, and I'm going to multiply that by the resistance, which is 10 ohms, and I'm going to find that gives us the same number within some error, I guess. I get about okay, I'll be honest, it's 1.44 times 10 to the negative 5th watts, and that's because I've been doing some rounding. But the powerful thing is here, you get, of course, you get the same answer, but you have to be really careful about what voltage drop you're using. You see why this is a little bit confusing? Okay, there's one last thing that I'd like to do. And now I want to say, what if instead, you remember this is our power lost. This is lost in distribution. Boy, that sounds like a cool movie name. Lost in Distribution. You should go see it. I haven't made it yet. Anyway, you should go see it. Lost in distribution. This is an extremely small amount of energy every second that's being lost because this is a very high voltage line. But what if instead, see, watch this. What if instead I take this voltage and I halve it? Watch as I cut that in half. I'm going to take 765,000 and I'm going to divide it by 2. What if my engineers decide that distributing power at this really high voltage is too expensive because I have to have towers that are extremely, extremely high, and maybe there's a citizen lobbying group that says that the magnetic fields at 60 hertz are going to be annoying or something? Great, sure they are. Yeah, I have a headache. Right. My point is this. If we take this power right here, I'm guessing that we'll get even more power lost, or we're going to get some significant power lost if we distribute at, what if this high voltage is 382,500 volts. Let's do that calculation right now. Again, I'm going to say that power to the load is 953 watts. So that means that that's the current in the wires times the voltage, the voltage of the wires, right? Relative to each other. The voltage drop across the wires, not the voltage drop due to the wires. Maybe I should say the voltage drop between the wires. Yeah, who knows? Anyway, what I'm planning to do here is I'm planning to find what the current would be. The current in the wires would then be, remember I'm going to get that voltage to be a little bit smaller, the current's going to be twice as big. So bear with me here as I take this voltage, the voltage of the wires, and divide it by the power to the load. And that power to the load divided by that voltage there divided by that power to the load, 953. We're going to get, ooh, something went wrong. What? Okay. How about I do algebra correctly? Watch as I do algebra correctly. I'm going to find that the current is actually the power divided by the voltage of the wires. Not that, it's not true. Okay, and in fact, I can take 953 and divide it by 382,500, boom. And I get a current that is just as expected, twice as what it was before. The current then in my high voltage line, that 382,000 volts, is 0.0025 amps. That means my power lost, remember these were equations of power lost, those equations of power lost are, well, we got I squared times R, and that gets us, we'll take that current right there, and I'll square it, and I'll multiply it by, remember we said our resistance was going to be 10 ohms. I wonder if you can still see these things. Oh, sorry. My apologies. So this thing here, 10 ohms, I'm going to take it and multiply it by 10, and that power loss is, whoa, that's a lot bigger, 6.2 times 10 to the negative fifth watts. But remember, I've got my naysayer who says that the power lost is voltage squared over R, but isn't that really big because this is a high voltage, and that's not the voltage that we need to use. We need to find the voltage drop across this line right here. And in order to do that, we have to find this voltage. In order to do that, we're going to say that the voltage drop of the wires is the current through the wires times the resistance of the wires. So the current through the wires is that number right there. I'm going to take 0.0025 and I'm going to multiply it by the resistance of the wires, which is 10. That voltage drop is 0.025 volts. Now I can take that number and square it and divide it by the resistance, and that resistance is 10. And I've gone around in a little math circle, but I've gotten you, again as we promised, 6.3 times 10 to the negative fifth watts. So we find that those are the same number. If you're careful, then you'll believe me that increasing the voltage of transmission lines decreases the current because P is IV. And if you decrease the current, then you get less lost in your transmission. Your transmission loss is that small, but notice if we just halved the distribution voltage, we got 4 times the loss in the lines. And that's because there's this square up in here. I'm talking about squaring the current, and if that current doubles, the current doubled between this situation and this situation, then we're gonna get 4 times as much loss. That's a really big deal. It means you can save 3/4 of your distribution costs if you double the distribution voltage. And that's why the wires are so high up above your head, because it's dangerous, because the voltage is so high, because it saves so much money that we should throw a party. Bye. So we want to go even further inside the wall. Watch with me. Inside the walls. Here we are. I wanted to know, so I went up to Wikipedia and I said, hey Wikipedia, how does power distribution work in your opinion? And they gave me this picture, and it's pretty, right? There's a generation station, there's a step-up transformer, and this is the weird thing. We want to understand why there's a step-up transformer, because these are expensive. You want to build a big, but I don't care. They're getting to a voltage that let's just go crazy. They're going to say this voltage right here, where I'm taking the voltage between one wire and the other wire, they're calling this voltage, let's go crazy, let's call it 765 25,000 volts. This would be the largest cross-country transmission line voltage. And then we get to a substation. So it's finally gotten to my town, and at that appreciate that. Then you gotta have a step-down transformer as well. Step up, step down, and then you've got customers over here, and the customer always knows about these gray boxes that are floating up in the sky. I call them the gray trash can floating in the sky, and I've got one near my house. And that brings us down from a certain voltage to here. So I'm just going to, I kind of translated this into my own. Thanks, Wikipedia. Let's get a box and paint it gray. That's gonna cost some money, right? So they're getting up to extremely high voltages. These voltages could kill a man. I tell you what, you walk within a half meter of those and you'll be killed. Wow, assuming you're in contact with the ground. Also, if you flew up on top of one and landed like a bird, you'd probably be okay because it's all about voltage difference. Anyway, then you gotta have, oh man, if you're gonna go to high voltage and you don't want little babies to stick their fingers in and die, thanks. Realistic though, it actually looks like this. There's a loop inside of a magnet, and that's what the power station is doing. I don't care how you're spinning it. What are you, burning coal and having the steam expand and spin the sucker around in some kind of a turbine fashion? You got yourself a wind turbine? Did you hire bums on the street and say, hey, crank this pedal, tough guy? Well, that's not cost effective, but it's a nice humanitarian effort. Then you got this step-up transformer. I don't know what the voltage is right here, but